picture for a moment the slow turning of a galaxy seen from far above, a soft spiral of light made of hundreds of billions of stars. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From this great height, the galaxy looks calm and finished, as if it has always been there and always will be. But the truth is gentler and stranger than that. Every star you see is somewhere along a long, slow story. Some are just beginning. Some are old. Some are quietly fading. And tonight, we wonder about that story together. Let your eyes drift across that pale spiral. Between the bright arms, you can see dark patches, like ink spilled across the light. These dark patches are not empty. They are clouds, cold, vast, and very still. Astronomers call them molecular clouds because the gas inside them is cool enough for atoms to join into simple molecules, mostly hydrogen, with a little helium and faint traces of dust. They drift through the galaxy for millions of years, doing almost nothing at all. And yet, inside these quiet clouds, every star that ever shone first began. Imagine sinking slowly into one of these dark places. The light of the surrounding galaxy fades behind you. The temperature drops. The space around you grows thick with the softest haze of gas, so thin it would seem like nothing on Earth, yet thick enough across light years to block the stars behind it. There is no sound, of course. Space carries no sound. But if there were a feeling here, it would be the feeling of patience. These clouds are old, and they are in no hurry. Here is where the mystery begins. We know that stars form inside these clouds. We have seen the young stars glowing from within them, still wrapped in their birth gas. We have seen the dusty disks spinning around them. And yet, we still do not fully understand what makes a cloud begin to collapse in the first place. A cloud can sit quietly for ages, then suddenly, in one corner, gravity starts to win. Something tips the balance. But what? That is one of the open questions we will sit with tonight. There are several ideas. One possibility is that a nearby star explodes, sending a gentle shock wave through the cloud, squeezing it just enough to start the collapse. Another idea is that the slow turning of the galaxy itself presses the cloud as it drifts through a spiral arm, like a soft hand closing around a handful of mist. Some researchers wonder if the clouds simply reach a quiet tipping point on their own, when their own weight finally overcomes the pressure of the gas inside. The evidence is incomplete. It may be that all of these things happen in different places at different times. We do not yet know which trigger matters most. What we do know is that once the collapse begins, it does not stop. Pockets within the cloud grow denser. Each dense pocket pulls in more gas. Each pocket begins to warm. The cloud breaks itself into many smaller knots, and inside each knot, a future star is quietly gathering itself together. A single great cloud can give birth to hundreds, even thousands, of stars in this way. They are born in families. Most will drift apart in time, scattered across the galaxy by the slow stirring of their orbits. Hold that picture in your mind. A dark cloud slowly waking. Inside it, 1,000 soft glows beginning to form. None of them are stars yet. None of them shine. They are still cold, still wrapped in dust, still gathering. It will take hundreds of thousands of years, sometimes millions, before any of them will burn. From our brief human point of view, the process is almost unimaginably slow. From the cloud's point of view, if a cloud could have one, it is happening quickly. This is where every star begins. Our own sun began this way about 4.5 billion years ago, inside a cloud that has long since drifted apart and forgotten itself. The atoms in your body were once part of such a cloud. The water in the oceans, the iron in the rocks, the carbon in every living thing, all of it once floated in a dark patch between the stars, waiting. Tonight, we follow that long story, from the first quiet stirring of a cloud to the soft glow of stars, yet unborn. And we sit gently with everything we still do not know. To understand how a star begins, it helps to picture the place where stars are born. We call it a nebula. A nebula is a vast cloud of gas and dust drifting through the dark space between stars. Most of the gas is hydrogen, the simplest and lightest element in the universe. A smaller portion is helium, and a tiny sprinkle of heavier elements like carbon, oxygen, and iron rounds out the mix. The dust is finer than smoke, made of microscopic grains of frozen water, carbon, and silicate minerals. These clouds are enormous beyond easy comparison. A single star-forming nebula can stretch across hundreds of light years. To picture that, imagine that light, the fastest thing in the universe, would still need 100 human lifetimes to cross from one side to the other. And yet, for all that size, a nebula is almost unimaginably empty. The gas inside it is thinner than the best vacuum we can create on Earth. If you scooped up a handful of nebula, you would hold mostly nothing, with only a few stray atoms drifting through your palm. The temperature inside these clouds is brutally cold. In the densest, darkest pockets, the gas can drop to just 10 or 20 degrees above absolute zero. That is colder than anywhere on Earth, colder than the surface of Pluto, colder than almost anything you can imagine. And in this cold quiet, something patient begins to happen. Gravity, the gentlest of all the cosmic forces, starts to pull the gas together. This is where the open question begins. We can see nebulae everywhere in our galaxy. We can watch young stars glowing inside them. But the exact trigger that nudges a particular pocket of gas into collapse is still debated. One idea is that a shockwave from a nearby exploding star sweeps through the cloud and squeezes part of it until gravity takes over. Another possibility is that the slow turning of the galaxy itself, with its great spiral arms, gently compresses the gas as it passes through. A third idea is that the cloud simply becomes too heavy in places and falls inward under its own weight. All three may be true in different cases. Researchers are still working out which trigger matters most and how often. Whatever starts the process, the collapse itself is slow at first. We are not talking about something that happens in a moment. A pocket of gas inside a nebula may take hundreds of thousands of years to draw itself together. The gas flows inward in long, lazy currents. The dust swirls along with it. Slowly, the center grows denser and the outer edges thin out. If you could watch the whole thing in fast motion, it would look a little like water spiraling down a drain. only stretched across an unthinkable span of time. As the gas falls inward, it begins to warm. This is one of the quiet wonders of gravity. When particles fall together, they speed up, and that motion shows up as heat. The cold cloud, once almost frozen, starts to glow faintly in the infrared. The center grows warmer than the edges. Pressure builds. The collapsing pocket starts to spin because almost everything in the universe spins a little. And as it shrinks, it spins faster, the way a skater pulls in her arms and turns more quickly. The size of these collapsing pockets matters enormously. And this is another place where the science is still being refined. Some collapse to form a single star. Others fragment into smaller clumps and form pairs of stars, or whole families of them. Most stars in the galaxy, in fact, are not lonely like our sun. They have siblings born from the same cloud, bound together by gravity for billions of years. Why some clouds make single stars and others make groups is still an open question. Computer models offer guesses, but the details remain unsettled. The raw material of a star is humble. Mostly hydrogen, a little helium, a trace of everything else. The numbers are almost the same across the universe. Roughly 3/4 of all the ordinary matter we can see is hydrogen, and about 1/4 is helium. Stars, planets, oceans, and bodies all draw from this same simple pantry. What changes is how it is arranged, and how hot it becomes, and what forces have shaped it over time. So tonight, picture that quiet cloud. Picture the cold gas drifting slowly. Picture gravity, gentle and patient, beginning the long, slow work of pulling something together from almost nothing. The collapse has begun, but the spark has not yet come. The cloud is waiting in the dark for what comes next. Inside the slow collapse, something quiet begins to change. The cloud has been falling for a long time, perhaps for hundreds of thousands of years, perhaps for 1,000,000. The center has grown denser, warmer, more crowded with falling gas. And now, deep within that crowded core, a new chapter is about to open. Not with a bang, not with light we could see from far away, but with a single, gentle event happening on a scale almost too small to picture. 2 atoms of hydrogen the simplest and most common matter in the universe, drift toward each other. Normally, they would not meet. The positive charges in their tiny hearts push them apart, like two magnets turned the wrong way. But in the heart of a forming star, the temperature has climbed to something close to 10 million degrees. At that heat, atoms move so fast that they can crash through their own resistance. They touch, they fuse, and in that fusion, a little energy is released. That tiny release is the first spark, not a flame in the way we imagine flames. There is no smoke, no crackle, no orange glow. There is only the binding of two small things into one slightly larger thing, and the leftover energy that comes flowing out. It happens once, then again, then in countless places at once, deeper and deeper through the core. A new kind of warmth begins to rise from inside. The conditions for this first spark are remarkably narrow. The core must be dense enough that hydrogen atoms cannot escape one another. It must be hot enough to overcome the natural pushing apart of their charges. And it must be steady enough to keep that heat from leaking away. If the cloud is too small, the core never reaches the needed temperature, and the protostar simply glows faintly for a while before fading. If the cloud is too big, the collapse can run away into something far stranger. The window for a true star to ignite is a balance held by gravity and chance. How long does this ignition take? The honest answer is that we are still working it out. Models suggest the steady fusion of a sun-like star may take tens of millions of years to fully settle into a stable rhythm. Before that, the young star flickers, brightens, dims, sends out jets, and gathers more material from its surroundings. There is no single moment when we can point and say, "Here, this is the instant a star was born." The birth is more like a slow waking up. The fusion begins in patches, then spreads, then steadies. One open question is how much the very first stars in the universe resembled this picture. They formed from clouds of pure hydrogen and helium, with none of the heavier elements that help modern clouds cool and collapse. Some researchers wonder if those first stars were enormous, hundreds of times the mass of our sun. Others suspect a wider mix of sizes, including smaller ones we have never found. first spark in those ancient cores may have looked nothing like the soft ignition we picture today, or it may have looked nearly the same, only on a grander scale. The evidence is still incomplete. What we can say is that fusion changes everything. Until that moment, the cloud has been falling inward, surrendering to gravity. Now, for the first time, something pushes back. The energy released by each fusion event spreads outward as heat and light, pressing against the inward pull. The star begins to hold its shape. The collapse slows. A balance, fragile but real, takes hold between the crushing weight of the outer layers and the bright resistance of the burning core. That balance is the heart of what a star is. Not a thing exactly, but a long argument between two forces, settled for a time. A truce that can last for billions of years, or only for a few million, depending on the size and makeup of the star. The first spark is the moment that truce begins. We do not know if every star ignites the same way. Some may stutter into fusion in fits and starts. Some may begin with a brief, brilliant flash that quickly settles. Some may never quite cross the line, becoming brown dwarfs, dim, warm objects that glow faintly without ever holding a true fire. The boundary between a failed star and a successful one is sharper than it sounds. And yet, there is much about it we still do not understand. For now, picture that single instant in the deep core. Two atoms meet. Energy whispers outward. Something has just begun that will shape worlds for ages to come. A protostar is not yet a true star. It is something quieter, something still gathering itself. Inside the slow collapse of a dark cloud, a thick, warm knot forms at the center, hidden from view. Around it, a wide spinning disk of gas and dust slowly settles into shape. From outside, you would not see a star at all. You would see only a soft, glowing cocoon, wrapped in layers of cold dust that hide its secret heat. The cocoon itself is made of simple things. Most of it is hydrogen, the lightest and oldest gas in the universe. Some of it is helium, a little heavier, also left over from the early years of time. Mixed into these gases are tiny grains of dust, smaller than smoke. The grains carry carbon, silicon, iron, and oxygen. They are the leftover ashes of stars that lived and died long before our sun was born. This is one of the gentle truths of the night sky. Every grain of dust in a stellar nursery was once part of something else. The iron inside it may have formed in the burning heart of a giant star that exploded billions of years ago. The carbon may have drifted out from a red giant as it slowly puffed away its outer skin. The oxygen may have been forged in fusion deep inside a star that no longer exists. A protostar is a recycler. It is gathering up the remains of older suns and trying to build a new one. The same atoms that swirl inside these cocoons also built the world you are lying on tonight. The iron in Earth's core, the iron in your blood, the calcium in your bones, the silicon in beach sand. All of it came from stars that lived before our sun. Our planet did not invent its own ingredients. It inherited them. A protostar today is doing the same slow work that built our home 4.5 billion years ago. Researchers still wonder about the exact recipe of these cocoons. The dust grains are very small, and they hide many of their details. One idea is that the grains form layers, like tiny onions, with ice coatings of water, methane, and ammonia wrapped around a rocky core. Another idea is that the grains grow by sticking together in slow, soft collisions, like snowflakes joining in still air. Both ideas may be partly true. The question of how dust truly grows in a stellar nursery is still open. Water is one of the most curious ingredients in the mix. We find it almost everywhere in these clouds, frozen onto dust grains as a thin shell of ice. When a protostar forms, some of this ice survives the heat. Some of it falls inward and is destroyed. Some of it stays in the cold, outer parts of the disk, where it may later become part of comets. Many researchers think Earth's oceans were partly filled by these icy travelers, arriving long after our planet first formed. The idea is not fully settled. The chemistry of the water in comets does not always match the chemistry of the water in our seas, so the question remains gently open. Some of our ocean came from the stars. How much? We do not yet know. Inside the cocoon, the protostar grows warmer and brighter, but it is not yet fusing hydrogen in its core. It shines instead from the heat of its own collapse, like a stone warming as it falls. Around it, jets of gas sometimes burst outward from the poles, punching through the dust in long, thin beams. Researchers can see these jets glowing softly in infrared light, even when the protostar itself is hidden. Why these jets form and how they shape the young star is another question that is not fully answered. The disk around the protostar is the place where worlds may someday form. Grains stick to grains. Pebbles join pebbles. Slowly, over millions of years, planets may take shape from the same dust that came from older stars. Everything in a planet, including the rock under your feet and the air you breathe, traces back through this long chain. The chain reaches from cooling neutron-rich shells of supernovae to the calm dust of a hidden cocoon, to the warm, rocky body of a new world. A protostar is a quiet pause in this long story. It is the moment when the leftovers of dead stars gather softly together, waiting to ignite. The cocoon is dim. The disk is patient. Somewhere inside, the first true heart of a star is forming, but it has not yet spoken. We are still learning to listen to what happens in that hidden space. Once a star catches fire in its core, something quiet and wonderful happens. The chaos of birth settles. The newborn sun finds a balance, and it holds that balance for a very long time. We call this long, steady chapter the main sequence. It is the longest stretch of a star's life and the most peaceful. For our own sun, it has already lasted 4.5 billion years, with about 5 billion more to come. To understand what is happening inside, picture two great forces locked in a slow, gentle wrestling match. The first force is gravity. Gravity pulls every speck of the star's gas inward toward the center. It never rests. It never lets go. If gravity worked alone, the star would crush itself into a tiny point in a matter of minutes. But gravity does not work alone. From deep in the core, fusion creates an outward push. The heat is unimaginable, around 15 million degrees in the case of our sun. That heat creates pressure, and that pressure pushes back against gravity with equal strength. The two forces meet somewhere in the middle of the star and cancel out. This quiet balance has a name. Astronomers call it hydrostatic equilibrium, which simply means the inward pull and the outward push are perfectly matched. If you could shrink down and float inside a main sequence star, you would feel this balance everywhere. Layer upon layer of glowing gas, each one pressing on the layer below, each one held up by the heat from beneath. The whole structure breathes very slowly, almost imperceptibly, as it adjusts to tiny changes in fuel and temperature. Stars are not solid. They are not really liquid either. They are vast, glowing seas of plasma, held together by their own weight and held apart by their own fire. Other forces play their parts too. Radiation pours out from the core in the form of light, and that radiation carries energy outward through the star's body. In the deepest regions, photons can take hundreds of thousands of years to travel from the core to the surface. They bounce, scatter, get absorbed, and get released again, inching their way through the dense plasma. The light you see from the sun today began its trip long before the first humans walked the earth. Closer to the surface, the star moves in a different way. Hot gas rises, cools a little, then sinks again, much like water boiling in a pot. These slow churning currents are called convection cells. On the sun's surface, we can actually see them as a pattern of bright cells, each one roughly the size of a country, bubbling and shifting in a constant, slow dance. There are quieter forces, too, ones we still do not fully understand. Magnetic fields thread through the star, wrapping around it, sometimes twisting into great loops that arch up from the surface. These fields can store enormous energy. They can release it suddenly in flares and storms. Why magnetic fields form the way they do, why some stars have gentle fields and others have wild ones, remains an open question. Some researchers think the spin of the star and the churning of its convection cells work together to generate these fields. Others think the picture is more complicated, especially for the smallest and largest stars, where the rules seem to bend. Then there are tidal forces, which only really matter when a star has a close companion. A nearby partner can stretch a star slightly, pulling its shape out of perfect roundness. over very long times, those tides can speed up or slow down the star's spin. They can even pass material from one star to another when the two are close enough to share an atmosphere. Lone stars like our Sun feel almost none of this. Their lives are simpler, slower, and more solitary. The truly remarkable thing about the main sequence is its patience. A star like our Sun changes very little across billions of years. Its brightness grows by only a small amount over those long stretches. Its color drifts only slightly. From the outside, you would barely notice anything happening at all. Inside, of course, atoms are fusing by the trillion every second, and energy is flooding outward in a quiet, ceaseless river. How a star finds this balance so reliably, and how it manages to hold it for so long, still inspires a kind of wonder among the people who study it. The forces are simple enough to name. The way they cooperate across millions of cubic kilometers of glowing gas, year after year, age after age, is something we are still learning to describe. For now, it is enough to know that a sleeping balance holds the stars steady above us tonight. Picture a candle in a quiet room. A bright candle burns hot and fast, eating its wax in a single evening. A small candle, set low, can flicker through an entire long night. Stars work in a similar way. The smallest, coolest stars in the galaxy burn their fuel so slowly that they live for almost unimaginable spans of time, while the brightest ones flash through their lives in what amounts to a cosmic afternoon. The smallest stars are called red dwarfs. They glow a soft orange or deep ruby color, and they are far cooler than our Sun. Their surfaces sit at around 3,000 degrees Celsius, compared to roughly 5,500 for the Sun. To the eye, if you could stand near one, it would feel less like a blazing fire and more like a giant, glowing ember floating in the dark. Their size is hard to imagine until you compare it to something you can hold in your mind. If our Sun were a beach ball, a typical red dwarf would be the size of a grapefruit, or sometimes even a small apple. The very smallest red dwarfs are not much bigger than the planet Jupiter, though they pack far more matter into that smaller frame. They are dense little furnaces, slow and patient, tucked into the corners of the galaxy. And there are so many of them. Some estimates suggest that roughly 3 out of every 4 stars in our galaxy are red dwarfs. They are the quiet majority, yet because they shine so dimly, almost none of them are visible to the naked eye from Earth. Look up at the night sky, and the bright dots you see are mostly the rare, hot, loud stars. The true population of the galaxy is hiding in the dark, glowing too softly to catch our gaze. The reason these little stars live so long comes down to a slow, careful kind of burning. A red dwarf has less hydrogen to begin with than our sun. You might expect that to mean a shorter life. The opposite is true. Because the star is smaller, its core is also cooler and less crushing. Fusion happens at a gentler pace, and because the star is fully churning inside, mixing its layers like a slow-stirred pot of soup, almost all of its hydrogen eventually reaches the core to be used as fuel. A larger star, like our sun, only burns the hydrogen near its center. The rest goes untouched. A red dwarf, by contrast, eats every last crumb of its supply very slowly over an enormous stretch of time. How long is that stretch? The numbers begin to lose meaning the moment you try to picture them. Our sun will live for roughly 10 billion years in its steady phase. A small red dwarf may live for 1 trillion years. Some of the smallest may last closer to 10 trillion. To set that next to something familiar, imagine a single heartbeat as 1 year of human life. 10 billion heartbeats would be the lifetime of the sun. 1 trillion heartbeats would carry you so far past the end of every sun-like star in the galaxy that the comparison breaks down entirely. Here is another way to feel the scale. The universe itself is only about 13.8 billion years old. Every red dwarf that ever formed is still alive. Not one of them, anywhere in the cosmos, has finished its life yet. They have barely begun. They are toddlers, still in the earliest moments of an existence that will outlast galaxies, outlast the formation of new stars, and stretch into a future so far away that the night sky we know today will be completely gone. There is an open question wrapped inside this slow burning, because no red dwarf has ever reached the end of its life. every prediction about how they finally die is based on calculation alone. The math suggests they will quietly fade, never swelling into a giant, never exploding. They may simply cool into small, dim objects called white dwarfs over countless more billions of years. Some researchers wonder whether the very smallest red dwarfs might behave in ways we have not yet imagined. We have models, but no examples. No star has yet shown us what that ending truly looks like. So when you look toward a small, faint red star tonight, you are looking at something that has just opened its eyes by cosmic standards. It will still be burning, gently and patiently, long after our sun has died, long after Earth is gone, long after the night sky has rearranged itself into something unrecognizable. And what its final breath will look like, no one yet knows. Imagine drifting through deep space, far from any familiar sun, until you come upon a star unlike the gentle yellow one that warms our days. This star burns blue, a deep, electric, almost violet blue, brighter than anything your eyes were built to see. If you could float a safe distance above its surface, the light would not feel like sunlight at all. It would feel like standing inside a furnace made of pure color, a glow so sharp it seems to hum. These are the blue giants. Some are 10 times the mass of our sun. Some are 50 times, or even more. Their surfaces churn with heat so intense that the gas there is not really gas in the way we usually picture it. It is plasma, atoms torn apart, their pieces drifting free, glowing white-hot at temperatures that can climb past 30,000 degrees. Our own sun, by comparison, simmers along at about 5,500 degrees on its surface. A blue giant is something else entirely. If you could hover above one, the view would feel strangely smooth from a distance. A vast, even sphere of brilliant blue-white light, almost too perfect, like a polished pearl lit from within. But as you drifted closer, the smoothness would break apart. You would see enormous convection cells, great swirling patches of rising and falling plasma, each one perhaps larger than a planet. The surface would shimmer with these slow, restless motions, glowing brighter where hot material rises, and dimmer where cooler material sinks back down. the colors are not really one color. There are pale blues, deep blues, hints of violet, and along the edges, a thin, trembling halo of light where the star's atmosphere fades into space. That outer atmosphere is its own strange place. Blue giants pour out streams of particles called stellar winds. But their winds are not gentle breezes. They are torrents. Some blue giants shed the equivalent of an entire Earth's mass into space every few years, blown away by the pressure of their own radiation. You would see this wind if you could watch in the right light. A faint glowing veil stretched out around the star like a soft cocoon of escaping gas. Some of these veils form delicate ring shapes. Some twist into spirals when the blue giant has a companion star nearby. The shapes drift outward slowly, fading into the dark, carrying pieces of the star away from it forever. And yet, for all this fury, blue giants do not live very long. Our sun has been burning steadily for about 4.5 billion years and will keep going for billions more. A blue giant might shine for only a few million years before its fuel runs out. By cosmic standards, that is the blink of an eye. The same enormous mass that makes them so bright also forces them to burn through their hydrogen at a furious pace. They are bright because they are dying quickly. This raises a question that researchers still puzzle over. Just how massive can a blue giant get before something breaks? There seems to be an upper limit, somewhere around 150 solar masses, though a few stars appear to push past even that. Why this limit exists is not fully settled. One idea is that beyond a certain mass, the star's own radiation becomes so strong it blows away any extra material trying to gather. Another idea is that the most massive stars we see today may actually be two stars merged together. The evidence is still being gathered, and the boundary remains blurry. There is also a softer mystery. The exact texture of a blue giant's surface, the size of those plasma cells, the speed of their churning, the way magnetic fields might tangle through them, is hard to study from so far away. We cannot send probes there. We can only read the light, and the light tells us much, but not everything. Some blue giants pulse gently in brightness, as if they were breathing. Why some pulse and others do not is still being worked out. So picture it once more before we drift onward. A vast sphere of blue-white fire, churning with slow, patient cells of plasma, wrapped in a glowing veil of wind, pouring out more light in 1 second than our sun pours out in months. Brief, brilliant, fated to end long before the small red stars we spoke of earlier have even finished their childhoods. The blue giant is a kind of cosmic candle that burns from both ends at once, and we still do not fully understand the rules that govern its short, luminous life. Our sun is a quiet, middle-aged star. It has been burning for about 4.5 billion years. It has roughly the same amount of time left before its calm life begins to change. To us, it looks like a smooth yellow disk in the sky. But beneath that bright surface, the sun is a deep and layered world, and much of what happens inside it is still being studied. The part we see is called the photosphere. It is not really a surface in the way that a planet has a surface. It is a thin, glowing layer of hot gas, only a few hundred miles deep. The temperature there is about 10,000 degrees Fahrenheit. If you could float just above it, you would see a churning sea of bright cells, each one larger than a country, rising and falling in slow patterns. These cells are the tops of huge currents that carry heat up from below. If you could sink beneath that bright skin, you would enter the convection zone. Here, hot gas rises and cooler gas falls, the same way water moves in a slow boiling pot. This zone stretches down for about 120,000 miles. It is wide, restless, and full of motion. Scientists can study its currents only by watching tiny shivers on the sun's surface, a method called heliosysmology. The word simply means listening to the sun, the way we listen to earthquakes on Earth. Below the convection zone lies a strange, quiet boundary. Researchers call it the tachocline. It is a thin layer where the churning gases above meet a calmer, more orderly region below. Many scientists think this thin layer is where the sun's magnetic field is born. But the details remain open. No one has seen the tachocline directly. We only know it must be there from the way the sun's outer gases spin at different speeds than its inner ones. Past that boundary, the gas no longer churns. It glows steadily in a vast region called the radiative zone. Here, light itself does the work of carrying energy outward. But the gas is packed so tightly that a single particle of light can take 100,000 years, perhaps even longer, to make its way through. The exact number is still debated because the path is random and the math is hard. The sunlight warming your window today may have begun its slow walk before the first human ever lit a fire. At the heart of all this lies the core. It is small compared to the rest of the sun, only about a quarter of its width. But it holds more than half of the sun's mass. The pressure there is unimaginable, and the temperature reaches about 27 million degrees Fahrenheit. In this dense, blazing center, hydrogen atoms fuse into helium, and a tiny fraction of their mass turns into pure energy. That energy is what feeds every layer above it. Every sunset, every shadow on a leaf, every warm afternoon begins in that hidden core. The strange thing is that we cannot see the core directly. No telescope can look into it. We learn about it by catching tiny ghost-like particles called neutrinos. These particles slip out of the sun's center and pass through the Earth, mostly without hitting anything. Detectors buried deep underground catch only a few of them. For decades, the number of neutrinos we caught did not match what our theories predicted. That gap was called the solar neutrino problem. It was eventually solved when scientists learned that neutrinos can change type as they travel. Still, our picture of the core is built from faint signals, careful math, and a lot of patient guessing. Some questions about the sun's middle age remain genuinely open. We do not fully understand why its magnetic activity rises and falls in cycles of about 11 years. We do not know exactly how the outer atmosphere, called the corona, becomes hundreds of times hotter than the surface below it. That puzzle is sometimes called the coronal heating problem, and several theories compete to explain it. One idea points to tiny magnetic flares too small to see one at a time. Another suggests waves of energy traveling along magnetic lines. The evidence so far supports parts of both ideas, and neither has settled the matter. So our middle-aged sun, the calm star that warms our days, is still a place of hidden depths. It hums with motion we cannot watch directly. It holds layers we can only guess at through ripples and ghost particles. It is familiar and strange at the same time, a steady companion whose quiet inner life is still being slowly, gently uncovered. Everything in the sky moves in cycles. Planets turn, moons orbit, tides rise and fall, and stars, too, breathe in their own slow way across millions and billions of years. A star is not a steady candle. It is a long, quiet rhythm of pressure and release, of fusion and rest, of one fuel giving way to the next. To understand what happens when a star begins to swell, we have to think in cycles that stretch far beyond a human life. For most of its long middle age, a star like our sun lives in a kind of balance. Deep in its core, hydrogen fuses into helium, releasing the warmth that pushes outward. Gravity pushes inward with equal strength. The two forces hold each other in a soft truce. This is the steady heartbeat we spoke about in earlier sections. But no truce lasts forever. Slowly, over billions of years, the core fills with helium ash. Helium is heavier than hydrogen, and it sinks toward the very center. The hydrogen that once burned there is used up. The core can no longer make the energy it used to. And here, something curious happens. The core does not cool. It contracts. As it contracts, it grows hotter still. The heat in this shrinking core travels outward into a thin shell of hydrogen that surrounds it. That shell, suddenly squeezed and warmed, begins to fuse far faster than the core ever did. The star is now burning hydrogen in a ring around a quiet helium heart. And the energy pouring out of that ring is too much for the outer layers to hold. So the star swells. Its outer skin drifts outward, pushed by the new flood of light from below. As the surface moves away from the core, it cools. The color of the star shifts from white gold to amber, from amber to a soft, deep red. The star is becoming a red giant. This swelling is not gentle in scale. A star like the sun can grow to many tens of times its current size. Some red giants stretch outward until until they would swallow the orbits of inner planets. The surface, though cooler to the touch than the original star, glows across a vastly larger area. So the total light pouring into space actually grows. A red giant is dim per square foot of surface, but enormous, and so it shines brightly across the galaxy. What fascinates many researchers is how irregular this swelling can be. Red giants often pulse. Their outer layers rise and fall in slow breaths that can take months or years to complete. Some of these rhythms are well understood. Others are not. The exact way a star transitions from steady middle age into this restless, swollen phase still holds open questions. How quickly does the change happen? How much mass is lost in the early swelling? How do magnetic fields shape the pulses? These remain active areas of study. There are competing pictures of what the inside of a swelling star looks like. One view holds that the helium core sits quiet and still, a dense ball waiting for its own ignition. Another view suggests the core itself may churn in slow currents we cannot yet see from outside. The light from the surface carries hints, but the hints are faint, and the models are not yet in full agreement. We do know that during this phase, the outer layers grow loose. The star's grip on its own skin weakens. A slow wind begins to blow off the surface, carrying gas and dust into the space around it. Over time, this wind can shed an enormous amount of material. The star, in a sense, is beginning to let go of itself long before any final ending. For our own sun, this swelling phase lies far in the future, several billion years from now. The sun will brighten gradually first, then begin its expansion. The inner planets will likely be lost. The outer planets will feel a warmth they have never known. What exactly will happen to Earth in those late stages is still debated. Some models suggest the planet is swallowed. Others suggest it drifts outward as the sun loses mass and survives, scorched but intact. This is the rhythm we are following tonight. A star is born from a quiet cloud, settles into a long, steady burn, and then, when its first fuel runs low, begins to swell into something larger, redder, slower, and stranger than what came before. The the cycle is not finished. The swelling is only the opening of a new chapter, one in which the star will keep finding new fuels to burn and new ways to change, until at last it cannot change any further. We will follow that chapter into the next section. A red giant is not a quiet thing. Its skin glows in deep amber and dusty rose, swollen far beyond the modest yellow ball it once was. If you could float beside one, you would see a surface that breathes. The whole star pulses in slow waves, swelling and shrinking over months and years. It is a soft, restless light, like a coal that will not quite settle. The size of a red giant is hard to picture. A star like our sun, when it reaches this stage, may grow until its outer edge reaches near the orbit of Earth. The mass has not changed much. The star has just spread out, like warm dough rising in a bowl. So the surface, even though it glows, is cooler than before. That is why the color shifts from white-yellow to a deep, gentle red. Because the red giant is so large, its gravity at the surface is weak. The outer layers barely hold on. A slow wind drifts outward from the star, made of gas and tiny grains of dust. This wind is patient. It carries pieces of the star away, year after year, building a soft shell of material that surrounds the giant like a faint halo. That halo is one of the most important parts of the story. The dust drifting out from red giants is where new chemistry begins. Carbon grains, silicate grains, tiny crystals of minerals. They form in the cooler outer reaches where the star's heat fades. Some researchers think much of the dust between the stars in our galaxy came from these slow red giant winds. Other ideas suggest supernovae play a bigger role. The balance between these two sources is still being studied, and the question of which one matters more in different galaxies remains open. A red giant rarely lives alone. Many stars are born with companions, and when one swells into a giant, the relationship changes. If the companion orbits close enough, it may find itself brushing against the giant's outer skin. Gas can spill from the larger star onto the smaller one. The two stars begin to share material in a slow, drifting exchange. Astronomers see these systems and try to model them. But the details of how the gas moves, how it cools, and how much of it sticks are still being worked out. In some cases, the companion is pulled deep into the red giant's outer layers. It spirals inward through the gas, dragging like a stone through honey. This is sometimes called a common envelope phase. What happens next is one of the more uncertain parts of stellar evolution. The two stars may merge into one, or the smaller star may eject the outer envelope and emerge in a tighter orbit. Computer models give different answers depending on the assumptions, and observations of the aftermath are still being gathered. Even without a companion, the red giant interacts with its planets. Any worlds that once orbited close in are likely swallowed. The expanding star reaches outward and engulfs them in a slow, glowing embrace. Worlds farther out drift to wider orbits because the star is losing mass and its gravitational pull weakens. Astronomers have found a few planets that seem to have survived a giant phase, clinging to existence at the edge. How common this survival is, and what such planets look like up close, is still being explored. The space around a red giant has its own gentle weather. The slow wind shapes itself into rings, arcs, and shells. Some red giants pulse in regular rhythms that send out repeating waves of dust. Others lose mass in sudden bursts, leaving uneven layers behind. When astronomers look at these shells with infrared telescopes, they see soft, nested structures like the rings inside a tree. Each ring is a record of a moment in the star's late life. Reading those records is a quiet kind of detective work. And there is the question of color. A red giant's surface is not one shade. It is patchy, with huge convection cells the size of planets bringing hot gas up from below. Dark spots and bright spots drift across the face. The whole pattern shifts on timescales we can almost watch. Why some giants pulse smoothly and others tremble unevenly is still being studied. The behavior of these enormous, turbulent surfaces does not always match the models, and that mismatch is itself a clue. So the red giant sits at the center of a small, glowing neighborhood. Its wind, its dust, its companion stars, its lost planets, its slow, trembling skin. It is not a single object, but a community, drifting outward and changing. What it gives away will, in time, become something else. For now, it simply glows, and we watch, and we wonder. Deep inside an aging star, in a place no telescope will ever see, something strange is thought to happen. It is sudden. It is violent. It is hidden. And in some ways, it is one of the most extreme events in the long, quiet life of a star like our Sun. We call it the helium flash. And even now, after decades of careful study, the full story of this moment remains partly a mystery. To understand why, let us drift back to the core of a red giant. The star has swelled. Its outer skin has cooled to a soft amber. But the heart, deep down, has been doing something unusual. It has been growing denser and denser, packing helium ash into a tight, hot ball. Helium is the leftover from millions of years of burning hydrogen. For a long stretch of the star's life, that helium just sits there, waiting, unable to burn at the temperatures it has. Then the core reaches a strange state. The matter inside becomes what some researchers call degenerate. That is a fancy word for a kind of squeeze so tight that the normal rules of gas no longer apply. In a normal gas, if you add heat, it expands and cools itself off. In degenerate matter, heat builds up without that release. The pressure does not rise with the temperature in the usual way. So when the core finally crosses the line into helium fusion, there is no gentle valve to let off steam. In a flash, an enormous amount of energy pours out. By some estimates, the core briefly produces power on the scale of an entire galaxy of stars. For a few seconds, deep inside that single dying sun, more energy is released than from 100 billion ordinary stars shining together. And yet, almost none of it ever reaches the surface. The outer layers soak it up. They puff and shift. From the outside, the star barely flickers. It is one of the most extreme events in the universe, hidden behind miles of glowing gas. This is what makes the helium flash so strange to think about. It is, by some measures, among the most powerful brief events a peaceful star will ever produce. And it leaves almost no fingerprint we can study from far away. We cannot see into the core. We cannot send probes. We can only model it with math and physics and trust that the models are close to right. But the models do not all agree. One picture suggests the flash happens in a single, clean burst at the very center. Another suggests it begins slightly off-center, where conditions tip first, and then spreads in a wave through the helium core. Some recent simulations hint at swirling currents, like storms inside the heart of the star, mixing material in ways the older simple models did not predict. Whether these currents are strong enough to change what the star becomes later is still an open question. There is more uncertainty too. We are fairly sure that stars roughly between half the sun's mass and about 2 times its mass go through a helium flash. Smaller stars never reach the needed conditions. Larger stars begin helium burning more gently before the core becomes degenerate. But the exact edges of these mass ranges and how the flash differs from star to star are still being refined. Each new generation of computer models nudges the picture slightly. There is even a quiet debate about how many flashes a star really has. After the main helium flash, some smaller secondary flashes may follow, like aftershocks. Their number, their timing, and how much they shape the star's later behavior are not fully settled. What we can say is this: somewhere out there tonight, in countless red giants scattered across the galaxy, these hidden moments are happening. A core no bigger than a small planet suddenly ignites with a brilliance we will never directly see. The star above takes a long, slow breath. Its outer layers settle. From the outside, nothing much seems to change. Inside, everything has changed. The star has crossed a threshold. It is now burning helium into carbon, slowly, steadily, beginning the next chapter of its life. It is humbling to picture. The most violent, quiet event in a sun-like star happens with no witness, no warning, no echo we can hear. It shapes what the star will become, how it will swell again, how it will eventually shed its skin, and it remains, in the deepest sense, a mystery we study from the outside, trying to read a story written in a language locked inside the stars themselves. For tonight, we can only rest with the wonder of it and let the question settle softly into the dark. When a dying star casts off its outer layers, it does not do so with violence. The shedding is slow, almost tender. Over thousands of years, the star pushes its skin outward in soft, expanding shells. These glowing clouds are called planetary nebulae, though they have nothing to do with planets. They got the name long ago, when early astronomers peered through small telescopes and saw round, fuzzy disks that looked a little like the pale face of a distant world. The name stuck, even after we learned the truth. What we are really seeing is the breath of a star at the end of its life. A small, hot core sits at the center, naked and exposed. It pours out ultraviolet light, and that light makes the surrounding gas glow in colors so gentle they seem almost shy. The shapes these nebulae take are strange and varied. Some look like rings, perfectly round, as if drawn with a careful compass. Others stretch out into hourglasses, with twin lobes flaring above and below a narrow waist. A few resemble butterflies with wide, feathered wings of gas, and some take on patterns so intricate, so layered, that astronomers still argue about how they could possibly form. This is one of the quiet mysteries of stellar death. A star is, in most ways, a sphere. It spins, it pulses, it shines outward in every direction. So why, when it sheds its outer layers, do those layers so often take on shapes that are anything but round? One idea is that a hidden companion star, orbiting close in, helps sculpt the gas as it flows outward. The gravity of that second star might pull the escaping material into a flattened ring, leaving the rest to escape upward and downward in twin streams. Another possibility is that the dying star has a strong magnetic field, which channels the gas along invisible lines of force. Both ideas have evidence behind them. Neither fully explains every shape we see. The colors are part of the wonder. Soft greens come from oxygen atoms that have been stripped of some of their electrons. Pale reds and pinks come from hydrogen, the most common element in the universe, glowing in the same gentle hue you would see in a quiet aurora. Blues come from helium, and deeper reds sometimes come from nitrogen and sulfur. Each color is a fingerprint of a specific element, lit up by the ultraviolet light pouring from the exposed core. To the human eye, these colors would look much fainter than the photographs suggest. The famous images we see are gathered over long exposures and gently enhanced. But the gases truly do glow in these tones. Inside many planetary nebulae, astronomers find small, knotty structures. These are sometimes called cometary knots because they have a dense head and a long, trailing tail that points away from the central star. Each knot is roughly the size of our solar system, and a single nebula can contain thousands of them. No one is entirely sure how they form. One thought is that they are clumps of cooler gas that survived the heat of the dying star, sheltered by their own density. Another is that they form later, as faster winds plow into slower ones and break the gas into pieces. The fine details are still being studied. The whole structure is fleeting. A planetary nebula lasts only a few tens of thousands of years before it dissolves into the wider space between the stars. Compared to the long life of the star that made it, this is barely a breath. If the star lived for 10 billion years, the nebula lasts about as long as a single afternoon in a human lifetime. We are lucky to see them at all. The galaxy holds only a few thousand of these glowing shells at any given moment, scattered like soft lanterns among the darker spaces. There is something gentle in the thought that a star ends not with a roar, but with a slow sigh of color. The hot core at the center will become a white dwarf, a topic for later. The gas will drift outward, mixing with the great clouds between the stars, carrying with it carbon and oxygen and nitrogen. The very atoms that future planets and future life may one day be built from. Why these shapes? Why these patterns? Why these particular soft hues? These are questions astronomers still turn over in their minds. The mystery is not loud. It does not demand attention. It simply waits, suspended in space, glowing quietly, asking to be understood. And for now, the answers remain partial, and the shapes remain beautiful, and the nebulae go on drifting in the dark. The The story of how we came to know white dwarfs begins not with a triumph, but with a puzzle. In the year 1844, the German astronomer Friedrich Bessel noticed something odd about the bright star Sirius. As he tracked its path across the sky over many years, he saw a slight wobble, a gentle side-to-side drift that no single star should make on its own. Bessel reasoned that some unseen companion must be tugging at it. He could not see this hidden partner, but the math was clear. Something heavy was there, dancing in the dark. For nearly 2 decades, that invisible companion stayed hidden. Then in 1862, an American telescope maker named Alvin Graham Clark was testing a brand new lens. He pointed it at Sirius, and there, tucked close to the blazing main star, sat a tiny, faint speck of light. It was the companion Bessel had predicted. They called it Sirius B at first. No one understood what they were looking at. The little star was dim, almost shy. Yet the gravitational pull it exerted suggested a mass close to that of our own sun. The riddle deepened in the early 20th century. Astronomers began to measure not just the brightness of Sirius B, but its temperature and color. To their surprise, the small star was actually quite hot, glowing with a soft white light. A hot star should be bright. A massive star should be large. Yet Sirius B was tiny and faint. The numbers refused to fit any familiar picture. If you packed a sun's worth of matter into a body roughly the size of Earth, the density became almost beyond imagining. A single spoonful would weigh as much as an elephant. Many astronomers simply could not accept it. The English astronomer Arthur Eddington admitted that the idea seemed absurd, even ridiculous. Matter, as everyone understood it then, should not behave that way. Atoms have empty space inside them, and that space should resist being crushed. Something was missing from the picture, and no one knew what. The answer came in the 1920s from a young Indian physicist named Subramanian Chandrasekhar. While on a long sea voyage from India to England, he worked through the equations of the new quantum theory. He realized that electrons, the tiny particles that orbit atomic nuclei, refuse to share the same state. When matter is squeezed hard enough, the electrons push back with a strange pressure that has nothing to do with heat. This pressure, born from the rules of the quantum world, could hold up a dead star against its own crushing gravity. A white dwarf, he showed, is a sun's worth of matter held aloft by this quiet quantum stubbornness. Chandrasekhar went further. He calculated that this pressure had a limit. Beyond a certain mass, around 1.4 times the mass of our sun, even the electrons would lose the fight. What happened after that, he could not say. At the time, his idea was met with cold skepticism. Eddington dismissed it in public, and the young physicist was deeply hurt. Decades later, Chandrasekhar would receive the Nobel Prize, and his limit became one of the cornerstones of modern astrophysics. Once astronomers understood what white dwarfs were, a new question quietly took its place. These small, dense embers no longer burn any fuel. They simply sit and glow with the leftover heat of their long stellar lives, slowly leaking that warmth into the surrounding dark. The cooling is gentle, almost unimaginably slow. A white dwarf the age of our sun would need many billions of years to fade from white to yellow, then to red, and finally to a cold, dark cinder. This is where the story becomes a mystery again. No one has ever seen a fully cooled white dwarf. The universe, at roughly 13.8 billion years old, is simply not old enough for any of them to have finished their long winding down. The coldest white dwarfs we observe still glow faintly. Their surfaces, somewhere around 4,000 degrees, the truly dead remnants, sometimes called black dwarfs, exist only as a prediction. Whether they will ever truly form and how long that cooling will really take remains an open calculation. There are other puzzles too. Some white dwarfs show traces of heavier elements at their surfaces, hints that they may be slowly swallowing the rocky remains of old planets. Some carry mysterious magnetic fields whose origins are still debated. Each of these soft, dim points of light carries a small, unresolved question, drifting through the galaxy at its own quiet pace, cooling on a timescale longer than the present age of everything we know. Inside every white dwarf, there sits a heart of carbon and oxygen. These are the ashes left over from a long life of burning helium. The star spent millions of years fusing one element into another. And when the fire finally went out, what remained was a dense ball of these two simple ingredients. The same carbon that forms the graphite in a pencil, the same oxygen that fills your lungs, packed together so tightly that a single spoonful would weigh as much as a small mountain. This is one of the stranger truths about the universe. The atoms that make up living things, the atoms that make up the air and the rocks and the oceans, were once squeezed inside the hearts of dying stars, and in many cases, they still are. Most of the carbon and oxygen in the galaxy lives quietly inside slowly cooling white dwarfs, waiting out the long ages. What makes these stellar hearts so strange is what happens to the matter inside them. The carbon and oxygen are not arranged like a gas, or even like a normal solid. The pressure is so extreme that the atoms lose their usual structure. The electrons no longer belong to individual atoms. They flow freely, packed together as tightly as the laws of physics allow. Scientists call this degenerate matter. It behaves in ways that feel almost impossible to imagine. It conducts heat like a perfect metal. It resists being squeezed further with a stubbornness that has nothing to do with temperature. There is another surprise hidden inside these stellar hearts. As a white dwarf cools over billions of years, some researchers think its carbon and oxygen may eventually arrange themselves into a kind of crystal. The atoms would lock into a regular pattern, like the structure of a diamond, but on a scale so vast it staggers the mind. A crystal the size of a planet, made mostly of carbon, sitting at the center of a dead star. Observations of certain old white dwarfs hint that this crystallization may already be happening. The evidence comes from subtle changes in how these stars cool and pulse. But the details remain open. We do not yet know exactly when the crystallization begins, how complete it becomes, or what mix of carbon and oxygen ends up locked inside. The question of that mix is itself a puzzle. The ratio of carbon to oxygen in a white dwarf depends on a single nuclear reaction that happened long ago, when the star was still fusing helium. That reaction, in which a carbon nucleus captures another helium nucleus to become oxygen, has a rate that is famously hard to measure. Tiny changes in that rate would change how much carbon and how much oxygen remain in the final heart of the star. Some researchers think the rate favors more oxygen. Others think the balance tips toward carbon. The question matters because it shapes the cooling, the crystallization, and even the eventual fate of the star. And it remains, after decades of careful work, one of the great open problems in nuclear astrophysics. There is also the strange matter of weight. A white dwarf with more mass is actually smaller than one with less mass. This feels backward. Pile more material onto a normal object, and it grows larger. Pile more material onto a white dwarf, and the extra gravity squeezes the whole thing tighter. Push the mass high enough, and the star approaches a limit beyond which it can no longer support itself. That limit, near 1.5 times the mass of our sun, is one of the cleanest numbers in all of astrophysics. What happens at that limit, though, is still being explored. Some white dwarfs in close pairs may pull material from a companion until they cross that line and explode. Others may collide and merge. The exact recipe for these endings is not fully settled. There are competing theories about which pathway is more common, and the answer affects how we read the light of distant supernovae used to measure the universe itself. For now, the carbon and oxygen hearts of dead stars sit in the dark, cooling slowly, perhaps crystallizing, perhaps holding secrets we have not yet learned to read. They are common. Our galaxy holds billions of them, and yet they remain, in many ways, strangers to us. The matter inside them obeys rules that only show themselves under conditions we cannot reproduce on Earth. We study them from far away, watching their faint light fade across the centuries, wondering what truly lies beneath that quiet surface. The mystery is not loud. It is patient, and it is waiting in the dark, slowly turning to crystal for as long as the universe permits. The smallest stars sip their fuel slowly, like a candle that burns for ages in a quiet room. The biggest stars are different. They live fast, glow fierce, and run through their hydrogen in only a few million years. first fuel runs low, they do something a star like our sun can never do. They press on. They reach deeper. They burn heavier and heavier elements in their cores, one stage after another, like a fire that keeps finding new things to consume. This is where the life of a star connects to almost everything else. The iron in your blood, the calcium in your bones, the oxygen in the air around you, the silicon in the sand on a quiet beach. All of it came from the cores of massive stars. The story of how big stars burn heavier fuels is also the story of how the universe filled itself with the stuff of planets and oceans and living things. The process begins with helium. When a massive star finishes its hydrogen, its core squeezes tighter and grows hotter. At around 100 million degrees, helium atoms start to fuse, 3 at a time, into carbon. This stage is shorter than the hydrogen stage. A star that spent 10 million years burning hydrogen may burn helium in less than 1 million. The clock is already speeding up. Then comes carbon, fusing at even higher temperatures into neon and magnesium. Then neon itself begins to burn, then oxygen, then silicon. Each new fuel demands a hotter, denser core. Each stage releases less energy than the one before, and each stage is shorter than the last. The hydrogen stage may last millions of years. The silicon stage, the final one, lasts only a day or two. A whole new chapter of the star's life passes between one sunset and the next. While these inner stages race forward, the star's outer layers swell into an enormous bloated giant. The surface may grow large enough to swallow the orbit of Mars or Jupiter, or even further out. Yet the listener watching from a great distance would see no sign of the chaos inside. The surface looks calm, red, slow. The frantic burning is hidden deep within. This is where the symphony begins. Massive stars are not lonely objects. They are part of a vast cycle that touches everything. As they burn, they push their outer layers outward in slow, heavy winds. These winds carry carbon and oxygen and nitrogen into the surrounding space, seeding the nearby clouds with the very elements that will one day form new planets. A massive star is, in a quiet way, a factory, and the galaxy is its patient customer. The light from these giants does its own work. It heats nearby clouds, lights up nebulae, carves bubbles in the cold gas around them. Sometimes that pressure squeezes other clouds into collapse, triggering the birth of new stars. So one giant, in its short, hot life, may quietly set off the creation of dozens more. There is still much we do not fully understand about this stage. The exact way mass is lost from a giant star's surface remains an open question. Some theories suggest steady winds. Others suggest sudden eruptions, brief and violent, that throw off whole shells of material in a single outburst. The truth may be a mixture. Observations of certain massive stars hint at both behaviors, but the timing and triggers remain unclear. Researchers also still debate how much each stage contributes to the elements we find in the universe today. Some heavy elements appear to be made mostly in massive stars during their fusion chain. Others may come more from the final explosion or from neutron star collisions far in the future of the star's life. Untangling these contributions is slow work, and the picture keeps shifting as new data arrives. What we can say with quiet confidence is that everything is connected. The carbon in a distant comet, the oxygen in a faraway ocean, the silicon in a grain of dust drifting between the stars. Each carries the signature of a giant that lived and died long ago. Every massive star that burns its way through these heavier fuels is writing a chapter in the chemistry of the cosmos. And every cloud collapsing tonight into new suns is reading from a book those giants wrote. The biggest stars do not just shine. They prepare the universe for what comes next. They burn through their layers, scatter their gifts, and leave behind the raw material for everything that follows. The story is still being studied, still being measured, still being slowly understood. For now, the great cycle continues quietly, patiently, in the deep dark above us. Inside a massive dying star, something quietly remarkable is happening. The star has become a kind of layered sphere, with different fuels burning at different depths. Picture an enormous onion glowing in the dark, each shell wrapped around the next, each one hotter and denser than the layer above it. This is the structure that that forms in the final ages of the most massive stars, and it represents one of the slowest, most patient transformations in the cosmos. Near the outer edges, hydrogen still burns. It is the same fuel the star used in its youth, and it has been burning there in one form or another for millions of years. Below that, in a deeper shell, helium fuses into carbon. Lower still, carbon fuses into neon. Beneath that, neon becomes oxygen. Oxygen becomes silicon, and silicon, in the deepest layer just above the core, fuses into iron. Each shell glows with its own quiet heat. Each one represents a different chapter of the star's long life, all happening at once. The strangest thing about these layers is how unequal their timescales are. The hydrogen-burning shell may have been active for 10 million years, the helium shell for perhaps 1 million. Carbon burning lasts only a few hundred years, neon burning less than a year, oxygen a few months, and the silicon shell, which makes iron in its furnace, lasts only a day or two. The star is racing through its final fuels faster and faster, even as the outer layers drift along almost unchanged. It is as if the deeper you look, the faster time seems to move. Astronomers cannot peer directly inside such a star. The layers are buried under thousands of kilometers of glowing plasma, hidden from any telescope. What we know about the onion structure comes from computer models, from the physics of nuclear fusion, and from the wreckage left behind after these stars die. The models agree on the broad picture. They disagree on many of the details. How sharp are the boundaries between layers? How much mixing happens between them? Do the shells stay neatly separated, or do slow currents stir them together like cream in coffee? One open question concerns the carbon shell. Some models suggest it burns smoothly, layer by layer. Other models hint that it can flicker, surge, and pulse, sending shockwaves through the star. These pulses might shake the outer layers and cause the star to shed material before it dies. We see hints of this in certain massive stars that throw off shells of gas in their last centuries. But whether those eruptions come from the carbon shell, from deeper layers, or from something else entirely, no one is sure. Another mystery is convection. In the deepest layers, hot plasma rises and cool plasma sinks, just like boiling water in a pot. These currents can carry fuel down into hotter regions, speeding up fusion. They can also carry fresh ash up and out, changing what the star looks like from outside. The size and shape of these convection cells inside a dying giant are still being studied. Different models give different answers, and the answer may depend on the star's mass, its rotation, and its magnetic field. The iron at the very center is the quiet heart of all this activity. Iron does not burn. When lighter elements fuse, they release energy. When iron tries to fuse, it absorbs energy instead. So the iron core just sits there, growing heavier each second, as the silicon shell above it dumps fresh iron onto its surface. The core has no way to push back against gravity. It is a clock counting down, though the star above it goes on shining as if nothing is wrong. From outside, the star may look almost calm. It may be red, swollen, its surface rippling with slow waves. Its light, gathered by patient telescopes, gives only faint clues about the layered furnace inside. Some elements show up in the spectrum, hinting at deep mixing. Other elements stay hidden. Astronomers have to guess at the rest, using the laws of physics as a kind of map. What strikes many researchers is how patient this process is, and how sudden its end. For millions of years, the star burns its hydrogen, untroubled. Then, in the last few years, everything accelerates. The layers thicken. The shells multiply. The core grows. And somewhere in the deep silence between the iron heart and the silicon shell, a threshold is approaching that no model can predict with perfect accuracy. We know roughly when it will come. We do not yet know exactly what triggers it, or why some stars cross that threshold differently than others. The onion is almost complete, and we are still trying to read its rings. Imagine a star so massive that it has burned through nearly everything it has. Its core is layered like the inside of an onion, with silicon turning to iron at the very center. From the outside, the star looks almost unchanged. It still glows. It still pours light into the dark. But something deep inside is about to fail in a way the star cannot survive. for most of its long life, this giant has shone in fierce blues and whites, hot enough to light up the gas clouds around it for many light years. Its surface temperature can climb above 20,000 degrees, far hotter than the soft yellow of our sun. That heat shows up in color. Cooler stars glow red and orange. Warmer stars shine yellow and white. The hottest stars burn with a steady blue so pure that it casts faint shadows of its own across nearby dust. Near the end, though, the color of the star can shift. Many of these dying giants swell into red supergiants first, their outer layers ballooning outward until the surface cools and reddens. The light that leaves them now is softer, almost the color of a dying coal. Some giants pulse slowly, dimming and brightening over months and years, as if the star itself is breathing. From far away, we can sometimes see these shifts in brightness. We watch the light wobble, and we wonder if the star is getting close to its final hour. This is one of the open questions astronomers still sit with. We do not yet know how to read the light of a doomed star with full certainty. Some supergiants seem to dim deeply in the months before they explode. Others appear calm right up until the last moment. The famous red supergiant in the shoulder of a familiar winter constellation darkened a few years ago, and many wondered if its end was near. The dimming turned out to be a cloud of dust the star itself had shed. The star is still there, still glowing, still mysterious. Inside the core, in the final hours, things move faster than the surface can show. Silicon fuses into iron, and iron is the wall that fusion cannot climb. Making iron does not release energy. It takes energy in. The fire that has held the star up for millions of years stops, paying its bill. The core begins to lose the battle against its own weight. But the light leaving the surface cannot tell us this directly. Photons born deep inside a massive star take a very long time to wander outward through its dense layers. By the time light from the core reaches the surface, the news is already old. The star can be quietly doomed for hours, even longer, while still shining as if nothing has changed. Some researchers wonder if there are subtle signals we have missed, tiny flickers or color shifts hidden in the noise. Others think the surface stays almost serene, and only the neutrinos, those ghostly particles that pour straight through matter, carry the true warning ahead of the light. There is something gentle about this idea. A star can be calm on the outside while its heart is already gone. The light we receive from such a star on the very night it dies may have left its surface before the collapse began. We are watching a memory. Then comes the silence. Not a true silence, since space carries no sound, but a pause in the story. The core falls inward in less than a second. The outer layers, still glowing in their old colors, hang briefly above an emptiness that has just opened beneath them. For a heartbeat, the star is hollow. The surface has not yet learned what has happened below. And then the light changes forever. A shock wave begins to climb outward through the layers, but that belongs to the next part of the story. For now, this section sits in the quiet just before. The blue or red glow steady on the outside. The iron core finished with its work. The neutrinos already racing ahead, invisible to our eyes, carrying the first true news of the ending. We still do not know exactly how to predict which star will go next, or when. We can list candidates. We can watch their colors and their slow pulses. We can guess at their masses and their ages. But the precise moment escapes us. Each massive star in the night sky holds a secret it will not share until the light itself arrives, long after the event. And so we look up, and we wait, and we wonder which of those steady points of light is already silent at its core, still shining only because the message has not yet had time to reach the surface. Space carries no air, and so a supernova makes no true sound in the way thunder rolls across a summer field. Sound needs something to travel through. It needs molecules to bump against one another, passing the pulse along. Between the stars, there are atoms, but they are spread so thin that a wave of pressure cannot really form. And yet, when a massive star finally tears itself apart, the silence is not the whole story. The blast sends shockwaves through the thin gas around it. Those shockwaves are, in a way, sound, just sound stretched across light years and slowed to a crawl no ear could ever follow. If we could somehow stand close to a dying star, we would not hear the explosion in any normal sense. The first thing to reach us would be light, a flash so bright it would outshine an entire galaxy for weeks. Then would come the wave of matter, gas, and dust hurled outward at thousands of kilometers per second. The shock would press against whatever clouds and bubbles already drifted nearby. Inside those clouds, atoms would crash into atoms. That crashing, if our instruments listened carefully, would carry a low rumble across the gas, a vibration we could record and slow down and turn into something like a hum. Astronomers do this kind of translation all the time. They take signals from space, radio waves, pressure changes, ripples in plasma, and shift them into the range our ears can sense. The result is a strange music, a supernova remnant centuries after the original blast still gives off this kind of song. The expanding shell glows in radio light, and when researchers convert those radio signals into audio, the sound is soft and grainy, like wind heard through a closed window. There is no single note. There is a wash of frequencies, layered, slowly shifting as the shell drifts and cools. What the explosion truly does, in a deeper sense, is seed the galaxy. Inside the layers of the dying giant, fusion has built heavier and heavier elements: carbon, oxygen, silicon, iron at the core. When the star collapses and rebounds, the violence creates conditions found nowhere else. In just a few seconds, atoms collide so hard that they fuse into elements heavier than iron, gold, silver, uranium, lead. These newborn atoms ride the shockwave outward. They mix with hydrogen and helium that already drift between the stars. They cool. They settle into vast clouds. And those clouds, given enough time, become the cradles of new suns and new worlds. This is the quiet meaning behind every supernova. The calcium in your bones, the iron in your blood, the oxygen in every breath. These atoms were forged in the cores of stars and scattered by explosions like this one. The sound of a supernova, if it has any sound at all, is the sound of chemistry being delivered. A slow, soft rush of new ingredients into the dark. But much about this seeding remains an open question. Researchers still wonder how evenly the heavy elements spread. Some studies suggest the blast does not mix smoothly. Instead, it sends out clumps and streamers, like ink poured into still water. Other studies suggest that nearby clouds can shield themselves, holding onto older material while the new atoms drift past. We do not yet know which picture is closer to the truth. We do not fully know how long it takes for a fresh supernova's gifts to settle into a new generation of stars. Estimates range from a few million years to many tens of millions, depending on the neighborhood. There is another mystery in the sound itself. The shockwave from a supernova is not a single clean pulse. It contains many smaller waves, smaller pressure changes, smaller eddies. Some of these may carry energy across enormous distances, gently stirring the interstellar gas, perhaps even helping to trigger the collapse of distant clouds into new stars. If that is true, then each supernova sings in a slow and almost inaudible voice to the clouds around it. And those clouds, swayed by the song, begin to fall inward and ignite. The cycle would close itself. Death would whisper birth into being. Whether that whisper is strong enough to matter is still debated. Some models say the push of a supernova helps star formation along. Others say it does the opposite, that the blast scatters gas too violently, blowing apart the very clouds that might have become suns. The truth likely lies somewhere between, varying from place to place, from era to era. For now, we listen to the slow music of remnants long after the explosion has faded, and we wonder what the song is really doing out there in the dark. When a massive star ends in fire, sometimes it leaves behind a tiny, quiet object that breaks the imagination. A neutron star. The core that survives the blast packs more weight than our sun into a sphere only about 20 kilometers across. That is roughly the width of a small city. And inside that small city sits more matter than our entire star. The numbers behind this object feel almost like poetry once you sit with them. A single sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. That is the weight of a mountain, folded into something you could hold in your palm, if your palm could survive it. Nothing in our daily life prepares us for that ratio, and yet the math is clean. The math is simple. The universe followed a few quiet rules, and this is what they made. A neutron star is born when the core of a dying giant collapses past the point where atoms can hold their shape. Electrons get pressed into protons. Together, they become neutrons, packed so tightly they almost touch. The whole core falls inward in less than a second. In that brief moment, gravity wins a contest it has been losing for billions of years. And the leftover ball of neutrons settles into a shape so dense it bends the space around it. The surface gravity on such a star is roughly 200 billion times stronger than Earth's. A pebble dropped from 1 meter above the surface would arrive moving at a fraction of the speed of light. Mountains, if they form at all, can only rise a few millimeters before the gravity flattens them. The whole surface is smoother than glass, smoother than anything we have ever measured in our own world. The spin is the part that feels like music. A young neutron star can turn hundreds of times per second. Some of the fastest ones spin more than 700 times in a single second. Picture an object the size of a city, heavier than the sun, turning that quickly without breaking apart. The reason it can hold itself together is the same reason it exists at all. Gravity at the surface is so strong that the spin, however fierce, cannot throw the matter loose. The numbers stay precise for an astonishing length of time. Some neutron stars keep their rhythm so well that astronomers can predict the arrival of their pulses to within a few millionths of a second, year after year. They have become the most accurate natural clocks we know of, more steady in some cases than the atomic clocks we build in our finest laboratories. A dying star transformed into a timepiece. The math of its rotation drifts so slowly that we measure the slowing in tiny fractions across decades. The exact upper limit of a neutron star's weight remains an open question. The math says there must be a ceiling, a point where even neutrons can no longer hold up against gravity, and the whole thing collapses further into a black hole. Most calculations place that ceiling somewhere between 2 and 2.5 times the mass of our sun. But the answer depends on what is happening deep inside the star the part we cannot see. And what is happening in there is not fully understood. Some theories suggest the very center is a sea of free quarks, the smaller pieces that normally hide inside neutrons. Other theories suggest strange new forms of matter that have never been made in any laboratory on Earth. Each theory predicts a slightly different maximum weight. Each one bends the elegant numbers in its own quiet way. The mystery sits at the heart of the densest objects we know, and the math alone cannot finish the picture. The distances involved are gentle in comparison. The nearest known neutron star drifts about 400 light-years from us. That sounds far, and it is. But on the scale of the galaxy, it is practically next door. Light from that star left around the time wooden ships first crossed long oceans on Earth, and it is still arriving tonight, faint and patient. The galaxy may hold 100 million such objects, scattered through the dark like seeds. There is something deeply restful about a universe that produces such things from a few simple rules. Mass collapses, gravity squeezes, neutrons hold the line until perhaps they do not. The rest is geometry and time. Out there, somewhere above us, in the slow turning of the night, tiny cities of impossible weight are spinning in silence, keeping time better than our finest clocks, and waiting for us to understand what their hidden centers are made of. Out of the violent end of a massive star comes one of the strangest objects in the sky. A neutron star spinning fast, sending out beams of light from its poles. When those beams sweep past Earth, we see a steady pulse. We call these spinning beacons pulsars. And while we have studied them for more than 50 years, we still do not fully understand how they shine. The picture in our minds is simple enough. A ball of neutrons, only about 20 kilometers across, turns on its axis many times a second. Two narrow beams of radiation pour out from its magnetic poles. If those beams happen to sweep across our telescopes, we hear a soft tick, tick, tick from across the galaxy. Some pulsars beat slowly, once every few seconds. Others spin hundreds of times each second, faster than a kitchen blender. What makes them so steady is hard to grasp. A pulsar can keep time better than most clocks we have ever built. Some of them drift by less than a billionth of a second over years of watching. That precision is almost beyond belief, coming from a star that just blew itself apart in a supernova. The balance feels almost impossible. Spin slightly faster, and the star might tear itself open. Spin slower, and the beams may fade away. Change the magnetic field just a little, and the whole performance shifts. The magnetic field is the part we understand the least. Pulsars carry magnetic fields trillions of times stronger than the field around Earth. We do not know exactly how those fields get so strong. One idea is that when the old star's core collapses, its weak field is squeezed into a tiny space, which packs the field lines tightly together. Another idea is that fast spinning and hot, churning matter inside the young neutron star act like a dynamo, building the field from scratch. Both ideas may be partly right. The full story is still open. Even more puzzling is how the beams form. We see the light. We can map its shape. But the engine that makes it is hidden from view. One theory places the source near the magnetic poles, where charged particles get ripped from the surface and flung outward along curved field lines. Another theory points to a region farther out, where the magnetic field meets the boundary of the spinning zone. Different pulsars may shine through different mechanisms. We cannot yet look inside one and check. The balance becomes even more delicate when you think about how easy it would be to break. A pulsar must keep its magnetic poles tilted away from its spin axis. If the poles lined up perfectly with the spin, the beams would not sweep, and we would see no pulse at all. There may be many silent pulsars out there, pointing the wrong way, hidden from us forever. We only see the ones whose geometry happens to favor Earth. That is a humbling thought. The sky we measure is only the slice we can see. Then there are the glitches. Every so often, a pulsar speeds up suddenly by a tiny amount and then slowly settles back. These small jumps may come from the inside of the star, where a strange, superfluid sea of neutrons shifts against the solid crust. We think the crust cracks, or the inner fluid slips, and the spin changes for a moment. The details remain murky. We are watching an object whose interior may be the densest matter in the universe, and we can only guess at what is happening below its surface. The fragile balance is also one of time. Pulsars slow down as they age. They lose energy through their beams, and through the waves they push out into space. After millions of years, the spin drops, the field weakens, and the pulses fade. The pulsar quietly becomes a dark, cold neutron star, drifting through the galaxy without a sound. Most of the neutron stars in the universe may already be silent. We catch pulsars only during a brief window of their lives, when everything is tuned just right. Some pulsars get a second life. If they orbit a companion star, they can pull in matter, spin faster, and start pulsing again at incredible speeds. These are called millisecond pulsars. How exactly the spin-up happens, and why some pulsars survive the process while others do not, is still being worked out. The whole family of pulsars feels less like a fixed type of star and more like a set of delicate states, each one balanced on a knife's edge. Tip the balance, and the lighthouse goes dark. For now, we keep listening to the ones that still shine. When a star is heavy enough, the end of its life leaves something stranger than a neutron star. The collapsing core falls past every limit we understand. No known force stops it. The matter shrinks down, and gravity grows so strong that even light cannot climb back out. What is left behind is a black hole, a place in space where the rules we know seem to break down completely. The outer edge of a black hole is called the event horizon. It is not a wall, and it is not made of anything solid. It is simply a boundary in space. Cross it, and there is no return, not even for a beam of light. From the outside, the event horizon looks like a perfect black sphere, ringed by the soft glow of hot gas falling in. From the inside, no one will ever send word back. That silence is part of the mystery. What lies past that edge is one of the deepest open questions in all of science. The math of general relativity says that everything that falls in is pulled toward a single point at the center, where density becomes infinite. This point is called a singularity. But most physicists do not believe singularities are real. They think the math is telling us something is missing. Some other theory, not yet finished, must take over inside the horizon. We just do not have it yet. One idea is that the center is not a point at all, but a tiny knot of space woven from the threads of quantum gravity. In this picture, matter does not crush down to nothing. It settles into a state we have no name for, held up by forces that only appear at scales smaller than an atom. Another idea suggests the inside of a black hole might be the seed of a new region of space, budding off from our own. Some researchers wonder if every black hole hides something like a fresh universe, sealed away forever. These ideas are beautiful, but the evidence is thin. They remain guesses dressed in equations. There is also the puzzle of what happens to the information carried by everything that falls in. Each atom that crosses the horizon brings a kind of fingerprint with it. Its history, its arrangement, its tiny details. The old picture said this information was simply lost. But the laws of quantum physics say information cannot be destroyed. So, which is right? This is sometimes called the information paradox, and it has been argued over for 50 years. Some researchers think the information is somehow stored on the surface of the horizon itself, like writing on a soap bubble. Others think it leaks out slowly over enormous spans of time, carried by a faint glow that black holes are thought to give off. That glow has never been measured. It is far too faint for our instruments, so the question stays open. Even the size and shape of the horizon hold quiet surprises. A spinning black hole drags space around with it, twisting the fabric of the universe like syrup stirred in a bowl. Inside that twist, time and space behave in ways that feel almost dreamlike. Some solutions of the equations even hint at strange shortcuts through space. But no one has ever found a real one, and most physicists doubt they exist. The math allows them. Nature may not. What we have seen with our telescopes is only the outside. A few years ago, a network of radio dishes spread across the Earth captured the first true image of a black hole's shadow, a dark circle ringed by warm light, sitting at the heart of a distant galaxy. It looked exactly the way the equations said it should. That was a quiet triumph, but the image showed us only the doorway. The room beyond remains hidden. For tonight, it is enough to picture that doorway. A perfectly round darkness, drifting in deep space, with a soft halo of gold and orange around it. Stars curve in long arcs as their light bends past it. Gas spirals inward in glowing ribbons. And at the center, something we do not yet understand waits in absolute silence. Whatever lies past that edge has been there for billions of years. It will be there long after we are gone. The black hole is, in a sense, the final chapter in the life of the largest stars. But it is also a beginning. It is the place where our current laws of physics seem to step aside, leaving space for a deeper theory we have not written yet. Somewhere out there in the dark, that theory is still waiting to be found. When a massive star ends its life in a bright explosion, it does not simply vanish. It scatters. The gas that once burned in its core flies outward in a slow, expanding shell, carrying with it the heavier elements forged during its long life. Carbon, oxygen, iron, silicon, calcium. These atoms drift back into the dark spaces between the stars, mixing with the older hydrogen and helium that already floats there. Over many thousands of years, this enriched gas cools and slows and settles into vast, soft clouds. And those clouds, in time, become the cradles of new suns. This is the gentle rhythm that astronomers call stellar recycling. Stars are born from the remains of stars. The atoms in a young sun today were once inside an older sun that died long before. And the atoms in that older sun were themselves inherited from an even earlier generation. The chain stretches back through deep time, all the way toward the first stars that ever shone. Each generation hands its dust to the next. Our own sun is part of that long line. The carbon in the trees outside your window, the oxygen in the air, the iron in your blood, the calcium in your bones. All of it was cooked inside some forgotten star and scattered into space before our solar system even existed. The cloud that became the sun was already rich with these heavier elements when it began to collapse around 4.5 billion years ago. We are, in a very real sense, the children of stars that died. What remains uncertain is exactly how this recycling works at the finer level. When a supernova explodes, the shock wave races outward into the surrounding gas. Some researchers think this shock can squeeze nearby clouds and trigger them to collapse into new stars. One possibility is that our own solar system began this way, jolted into formation by the death of a nearby giant. Another idea is that most new stars form more quietly, without any nearby explosion, simply through the slow pull of gravity on cold gas. Which path is more common, and which path made the sun, is still an open question. The far future will follow the same pattern, but on a much grander scale. In about 5 billion years, our sun will begin to swell into a red giant. Its outer layers will drift away as a soft, glowing shell, painting the sky around it in pale colors. The core will be left behind as a white dwarf, slowly cooling for a very long time. The gas it sheds will join the wider clouds of the galaxy, mixing with the remains of countless other stars. Somewhere, perhaps tens of millions of years later, that gas may collapse again and form a new sun with new planets and perhaps with new oceans. Long before that, the Earth itself will have changed beyond recognition. The continents drift only a few centimeters each year, but given enough time, those small motions add up. In a few 100 million years, the familiar shapes of the continents will be gone, replaced by new arrangements we cannot fully predict. The oceans will rise and fall. Mountains will lift and erode away. The sky will look different too, as nearby stars drift slowly through their orbits around the galaxy. On still longer scales, the Milky Way itself will change. Our galaxy is slowly approaching its neighbor, the Andromeda Galaxy. In about 4 billion years, the two will begin to merge. The stars within them are so far apart that almost none will collide. But the great clouds of gas will mix and stir, and the disturbance may spark a new wave of star birth. New suns will light up in regions that, for now, are mostly quiet. How long this cycle can continue is another open question. Star formation in the universe peaked billions of years ago and has been slowly declining ever since. Some researchers think galaxies will keep making stars, more and more slowly, for trillions of years to come. Others suggest the gas will eventually run thin, and the last new stars will be small, dim, red dwarfs that linger for an unimaginably long time before fading. The very last starlight may shine in a universe that is mostly dark. For now, though, the recycling continues. Somewhere in the galaxy tonight, an old cloud is quietly collapsing. Somewhere, a young protostar is gathering its first warmth. And somewhere, the atoms of a star that died 1 billion years ago are drifting into the place where a new sun will one day shine. The universe is always becoming something else. The question of where this slow becoming finally leads remains unanswered and beautifully open. Step back with me for a moment. Step back from the burning surfaces and the slow collapsing clouds, back from the white dwarfs cooling in the dark, back from the neutron stars spinning in their quiet corners of the galaxy. Let your mind drift up and outward, past the spiral arms, past the dust lanes, until the whole story of stars sits before you like a single long breath the universe is taking. From this distance, every star is a chapter in one enormous story. And in that story, we still do not know how many of the endings really work. We have ideas. We have models that match much of what we see. Yet the deeper we look, the more open questions we find. Why do some stars of nearly the same mass end in such different ways? Two stars can be born side by side in the same cloud with almost the same weight. One becomes a quiet white dwarf. The other tears itself apart in a supernova. Small differences in spin, in magnetic fields, in companions, in chemistry, seem to tip the scales. But the exact rules remain blurry. The boundary between a neutron star and a black hole is another soft place in our knowledge. Somewhere along the line of mass, a collapsing core stops being a neutron star and becomes something darker. Where exactly does that line sit? Some researchers think it may shift depending on how fast the core spins. Others wonder if there are exotic stars in between, made of strange matter we have never touched. The evidence is incomplete, and the question stays open. Even the simple act of explosion holds secrets. For decades, models of supernovae kept failing to explode in the computer. The shock wave would stall. The star would not blow apart on the screen the way it clearly does in the sky. Newer simulations with better physics do better. Yet the full picture is still being pieced together. Why do some massive stars explode brightly, while others seem to vanish quietly into black holes without much of a flash at all? The question remains open. And what of the rare, strangest endings? Some explosions shine for months with a brightness no ordinary supernova should reach. One idea is that a powerful young magnetar inside is feeding the blast with its spin. Another is that the dying star collided with shells of gas it had thrown off long before. Both ideas could be partly right. Neither is settled. Step further back still. Look at what these endings have done over billions of years. The first stars, born from pure hydrogen and helium, built the first heavier atoms in their hearts. When they died, they scattered those atoms into the dark. Later stars formed from that enriched dust and built heavier things still. Generation after generation, the galaxy slowly grew richer in carbon, in oxygen, in iron, in gold. You are part of that long inheritance. The calcium in your bones was forged inside stars that died before the sun was born. The iron in your blood was scattered by ancient explosions. The oxygen you are breathing right now passed through the fiery cores of giants, whose names no one will ever know. In a very real sense, you are starlight that has cooled and learned to think. And yet, even this part of the story holds its mysteries. We do not fully know where every element comes from. For a long time, researchers thought most of the heaviest elements, like gold and platinum, came from supernovae alone. Then came new evidence that colliding neutron stars may forge much of it instead. The balance between these sources is still being worked out. Each new observation shifts the picture a little. There are deeper mysteries underneath. We do not know if the laws that guide stars have always been exactly the same, or whether they drift by tiny amounts over cosmic time. We do not know if some stars in the early universe behaved in ways we have never seen since. We do not know what the very first stars truly looked like, because none of them remain. only their echoes are left, written in the chemistry of older galaxies. From this wide view, the life cycle of stars is not a finished textbook. It is a living question, still being asked, still being answered, still being revised. And you are inside the question. Your atoms have been through it. Your body is a slow, warm record of stellar deaths going back billions of years. Rest in that thought for a while. The sky above you is not separate from you. It is older family, and much of its story is still unwritten, still waiting in the quiet, patient dark. We have followed the long arc of a star together, from its quiet beginning inside a cold cloud to its many possible endings. We have stood beside red dwarfs that may outlive the universe as we know it, and watched in our minds as blue giants burned themselves out in only a few million years. We have wondered about white dwarfs cooling for ages we cannot measure, and about neutron stars spinning at the edge of what matter can survive. We have looked toward black holes and admitted gently that we still do not know what lies beyond their dark rim. And now, slowly, we let all of that go. Picture, for a moment, a small blue world turning in the dark. Its oceans are calm. A single moon hangs over the water, pale and patient. The starlight reaching that ocean has traveled for thousands of years to be there, carrying with it the memory of a star that may already be gone. The light does not know this. It simply arrives, soft and silver, and rests on the waves. The whole galaxy is doing this. Every second, in every direction, light is leaving stars and crossing the long emptiness between them. Some of it will fall on planets. Some of it will pass through clouds of dust and warm them gently. Some of it will travel for so long that whole civilizations could rise and fade before it ever lands anywhere at all. The universe is full of this slow, quiet traffic of light, and most of it will never be seen by anyone. That is not sad. It is simply the way of things. Far in the future, long after our sun has cooled into a small white ember, new stars will still be forming in quiet corners of the galaxy. Cold clouds will gather. Gravity will pull them inward. A new spark will catch, and another small sun will begin its long, steady work. The cycle will continue without us, and without anyone needing to watch it. And that, too, is a kind of peace. How long this can go on remains an open question. Some researchers think star formation will slow to a trickle over trillions of years, until the last red dwarfs glow faintly in a darkening sky. Others wonder whether new clouds, gathered from the wreckage of old stars, might keep the lights on far longer than we expect. No one knows the final chapter. The universe has not finished writing it. For tonight, none of that needs to be settled. For tonight, it is enough to know that you are lying here on a small, warm world, on the surface of a planet that is itself made of stardust. The iron in your blood, the calcium in your bones, the oxygen in every slow breath you are taking right now. All of it was forged inside stars that lived and died long before the sun was born. You are, in the most literal sense, made of old starlight. And when you breathe out, you are returning a little of that ancient material back into the air of the world. The galaxy turns slowly above you. It does not hurry. It has been turning for billions of years and will turn for billions more. There is no deadline in the sky. There is no urgency among the stars. They form when they are ready. They shine for as long as their fuel allows. They end in whatever way their mass decides. And then their dust drifts on, ready to become something else, in some other quiet corner, in some other quiet age. You are held inside all of this. Small, yes, but not separate. The same gravity that shapes the galaxy is holding you to your bed. The same elements that burn inside distant suns are warming inside you. The same long patience that built the stars is the patience that lets your breathing slow, and your shoulders soften, and your thoughts drift. Somewhere out there, a red giant is shedding its outer layers in soft, glowing rings. Somewhere, a young star is taking its first uncertain breath inside a dark cloud. Somewhere, light that left a sun before humans existed is just now arriving at an empty shore on a world we will never name. All of it is happening right now while you rest. The mysteries will still be here tomorrow. The questions are in no hurry, and neither are you. Let the stars keep their secrets for one more night. Let the galaxy turn without you. Let the long, gentle future of starlight unfold somewhere far away, while you stay exactly here, exactly safe, exactly still. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet